All right, so in example 5, we're just going to use the result we just found and find the sums of these geometric series if they are geometric. So we're asked to identify which of the following are geometric, and those that are geometric, we want to find the first term, the common ratio, and the sum if it exists. And if it's not a geometric series, we're asked to explain why. All right, so the key thing to remember is that a geometric series has a common ratio. So if we just take the ratio of consecutive terms, we should get a constant amount. So if we take 1/9 over 1/3, right, that's 1/3. 1/27 over 1/9 is 1/3. So if we take the ratio of consecutive terms, we always get the same common ratio. So this is definitely geometric. So in the a value, that's just our first term, right? So that's 1/3. And our r is also 1/3, right? Because we're just taking each term in the sequence and multiplying it by 1/3 to get the next term, right? So our common ratio is 1/3. And since it has a common ratio, it is geometric. Geometric. Okay. Now let's find the sum. So the sum is equal to, I have it right up above, it's equal to the a value, so 1/3, over 1 minus r. So that's 1 minus 1/3. So basically it's 1/3 over 2/3, which we can also write as 1/3 times the reciprocal of 2/3, which is 3/2. And so what we get is 1/2. Now I also want to show you, this is another one where there's a nice geometric picture for it. All right. Now, do you see how this is showing that 1/3 plus 1/9 plus 1/27 and so on equals 1/2? So you can see it's kind of spiraling around. I'm taking, so the whole rectangle represents 1, and then I've colored a 1/3 of it green, right? So essentially this first large green rectangle is 1/3 of the whole rectangle. And then I've taken 1/3 of a third. So in this middle section, I've divided into thirds and I've colored 1/3 of it green, right? And then I took 1/3 of a third of a third and colored it green. And then, let's see, a third of a third of a third of a third and colored it green, and so on. And you can see this thing spiraling around. And on the other side, I've colored it 1/3 blue, and then 1/3 of a third blue, and 1/3 of a third of a third blue, and you can see how we have these intertwining spirals, right? And these spirals are symmetric, and they are so they're basically the same size. So if you add up all these thirds and thirds of thirds and thirds of thirds, thirds of thirds, you get 1/2. So all right, that's awesome, right? All right, let's go on to the next example. All right. So we want to find out if this is geometric. Well, all right, let's start writing out some terms here. Now when I put in n equals 1, right, n minus 1 is 0, so I just get 0. And I put in n equals 2, 2 minus 1 is 1, 1 cubed is 1, so I get 2. And then the next term then will be, so I get 1, n equals 3, right? So 3 minus 1 is 2, 2 cubed is 8, 8 times 2 is 16. All right, so you can see first of all that it's certainly not going to 0. It keeps getting bigger. The next term is 54, and it just keeps going on. Now, but we can have a geometric sequence that doesn't converge, right? That diverges. But what the key thing is that we need a common ratio. So if we look at consecutive terms, 2 divided by 0, well, that's nothing. 16 divided by 2 is 8. 54 divided by 16 is certainly not 8. So the problem is we don't have a common ratio. So there's no common ratio. And if it doesn't have a common ratio, then it is not geometric. Okay, so that one is not a geometric series. All right, got a couple more here to look at. Now, some of these, initially you look at them, it's like, well, I don't know. But let's try and rewrite this one. So I'm just going to rewrite this. So I'm going to copy down the summation from n equals 1 to infinity. And, I've got a power of n, or a power of 2n on the top, and a power of n minus 1 on the bottom. So I'm not, this common ratio is not jumping out at me, but if I manipulate it a little bit, I might be able to do something with it. So this essentially is, in the numerator, it's 2 squared to the n power. So really it's the same thing as 4 to the n. So I can rewrite this as 4 to the n over 3 to the n minus 1. Now, in order to get a common ratio, I would really like to have a factor that has the same power. But in this case, I've got n and I've got n minus 1. But I can actually rewrite the numerator. So I'm going to copy this. N equals 1 to infinity. I can write 4 to the n as 4 times 4 to the n minus 1. Okay, that's the same thing. And then I could just write it here. I have 3 to the n minus 1 in the denominator. But I can actually pull that 4 out front. So now you can see if I just combine those, the numerator and denominator that have the same power, right? So let me copy this down. So what I have is 4 times 4 thirds to the n minus 1. So we do have a common ratio, right? We have this multiplier of 4 thirds. So our sequence is going to look like 4, and then the next term is essentially going to be 4 thirds times that, which is 16 thirds, and the next term then will be 64 ninths, and so on. So our first term is equal to 4, and our common ratio is equal to 4 thirds. All right, so it is geometric, but our common ratio is greater than 1, so it diverges. Because this R value is greater than 1. Okay. All right, we've got one more to look at. So this one, we've got 3 to the n plus 1 times 1/4. Okay, so we want to reframe this in terms of a first term times some multiplier. So let's rewrite this. I'm going to take this. I'm going to take my 3 to the n plus 1. I can write that as 3 to the n times 3. Or I could flip it around, and 3 times 3 to the n. It's probably easier that way. So if I take 3 times 3 to the n over 4 to the n, right? Because 1/4, 1 to the n is just 1, and then so I could write this as 1 over 4 to the n. So really, this is what it looks like, right? So n equals 1 to infinity. If I rearrange it, it looks like that. Now I could even clean it up a little more. N equals 1 to infinity. I could write it as 3 times 3/4 to the n. All right, so we have a, you can see we have a common ratio. Now you have to be careful, because what is your first term? So let's just put in n equals 1, because you might be tempted to say, oh, my first term is 3. But it's not, because the first term, when n equals 1, it's going to be 3 times 3/4, so it's going to be 9/4. Okay, and then we're just multiplying by 3/4 every time, so it's going to be 27 over 16, right? And then plus 81 over 64, and so on, right? So our first term is 9/4, and our common ratio is 3/4. So it is geometric because it has that common ratio. And is the sum going to converge? Well, my R value is less than 1. So yeah, and so I can write the sum is equal to 9/4 over 1 minus R, so 1 minus 3/4. 1 minus 3/4 is 1/4. Reciprocal of that is 4. So essentially it's 9/4 times 4, which is just going to be 9. So there you go. We have the sum of an infinite geometric series. So I got one more example, looks like, to go over, and then you'll be ready to work on the discussion questions.